In this video, we're going to look at exponential equations and logarithm properties. So to start off, let's look at this relationship between exponentials and logarithms. So here we have an equation. This is an exponential equation. We got some base b, could be any number, 5, 10, 30, whatever. Some number to the x power equals y. And this is just asking what is the power we put on b to get y. Well, this logarithm statement here is saying the same thing. So when we say the logarithm base b of y is equal to x, we're saying what is the power we can put on b to get y. Okay, so this is, when you read a logarithm, this is the question that we're asking. What is the power of base b that it takes to get the value of y? And so the key is when we're finding a logarithm, it's a power we're looking for. Okay, we have some other little identities that will be useful that we'll see along the way. So we'll come back to that one. So let's start by understanding logarithms on our equation here. Logarithms are the key to solving these exponential equations. So using our calculator, we can do two things. We can do a log base 10 of x or log base e. E is Euler's number. And this Euler's number is a number that just shows up a lot in nature. It's about 2.718. Okay, so on your calculator, these two things are written a little differently. On your calculator, log base 10 of x should just show up as log base x. So when there's no number written down here, we understand it to be log base 10. The natural logarithm, as is written right here, if we have log base e, well, that's going to be ln of x. All right, the natural log of it. So let's see how we use that real quickly here using the definition of a logarithm. So here we have an equation, 10 to the x equals 110. Well, this is just asking, what is the power we put on 10 to get 110? Well, that's basically saying we're looking for the log base 10 of 110. Because once again, this is saying, what is the power we put on 10 to get 110? 10 to the x equals 110. Notice the base here is 10, the base here is 10. And so we use our calculator. You can plug that into our calculator, and we'll get an approximation. And plugging it into our calculator, we get that x is approximately 2.04, which is what we expect because I know that 10 to the second power is 100, and so this is going to be a little bit bigger than the second power. Okay, well, let's use the same idea over here on b, and you can try it out. You can pause this and try it out, see what you get. And what you should get is something like this. Again, let's rewrite log base 10, because that's our base, of 0.005 is x. Using our calculator, we get that x is approximately negative 2.30. And again, that's what we expect because this is a small number. So 10 to some negative exponent, okay, will give us a fraction, 1 over 10, and that's going to give us this. Okay? How about this next one? Well, let's try dividing by 3 first. So if we divide this by 3, before we take the logarithm, we have 10 to the x equals, and that gives us 71. And now we're just looking for the log base 10 of 71, because x is the power that we put on 10 to get 71. Using our calculator, we get 1.85. So pause the video and try the next 3 here on your own, and then come back and see how you did. So for d here, we get log base 10 of 0.5 is 4x. Using our calculator, we get negative 0.301 equals 4x, and that we can finish off with a little dividing. So we have one more step after we take the logarithm in this case. And this is going to give us x equals negative 0.05. All right. Here, now we got base e, so this is log base e. And if you really wanted to, you could write log base e of x. Actually, let's fix that. Let's make that log base e of 23, because x is the power. So the log of 23 is x. But more typically, we'll write this as ln, natural log of 23, equals x. And we just use our calculator to get an approximation. This gives us 3.14. And no, it's not pi, but it looks close. So here, let's do it all. Let's divide by 2. And we get this. Take the natural log of 12. That's going to be x plus 2, because x plus 2 is in the power. And we can subtract 2 from both sides, and we get x is the natural log of 12, which there's the exact answer, but let's get an approximate answer here. End up with 0.485. All right. Well, that's the foundations there for logarithms. Now let's apply them to exponential equations. And let's start with a little exploration here. Here we have a bunch of logarithms, and we just want to use our calculator to explore a little bit and see what you get here. So go ahead and pause the video for a moment, try these out, and see if you get the same idea, same answers that we end up with here. So after some careful input in your calculator, you should get these numbers here, 1.176 and 1.176. Negative 0.2218, and the same thing over here, 2.386 and 2.386. Okay, so it was rigged here. It was set up, obviously. So we see that there's some connections here. And by the way, we might note that we could do this with a natural log. So trying this with a natural log here, the first one. And by the way, the parentheses are real important here. You got to be careful how you enter this in your calculator. We get 2.708. And if you enter this in your calculator, make sure you close the parentheses around the 3. A lot of calculators, you need to have these parentheses here and parentheses there. So that will give us the exact same thing. It's also 2.708. So what's going on? Let's check this out. So let's try generalizing this a bit here. And let's say that, let's define this. Log base b, well, that's kind of big. Let's say the log base b of capital P equals little p, log base b of capital Q is little q. So using what we know about properties of logarithms, we can say that by swinging around, putting this b under the exponent here, putting this b under the exponent here, we end up with capital P is b to the little p, capital Q is b to the little q. Now let's use that to figure some things out here. Let's say we have y is equal to log base b. B is just any number, any positive integer here, of p times q. Well, all right, so we know that this gives us, we could rewrite as b to the y equals capital P times capital Q. All right, and that we could write like this. B to the y equals, now from up above, capital P is b to the p and capital Q is b to the q. So let's substitute b to the little p times b to the little q. But we know that when we are multiplying with the same base here, we add the exponents. And so we have, this is just b to the p plus q. So what this is saying is that, well, let's add in this, our left side, b to the y. Okay, so this y here is equal to p plus q. Okay, so y is equal to little p plus little q. Well, little p and little q are just substituting from up here. Little p and little q are these logarithms. So we end up with log base b of capital P plus log base b of capital Q. All right, so we've proven there that this is true. Okay, let's try another one. Before we go too far, though, let's see what we have. So here we're multiplying p and q, and here's the log of p and the log of q, and that's what's going on in the top one here. Okay, we can write this product as a sum, because remember, when we're finding logarithms, we're talking about the exponents. The log is the power. All right, so let's do the same kind of idea here. Let's rewrite this. Let's swing around the base and write it as an exponential. B to the y equals, and we've got this capital P divided by capital Q. So now we're dividing. Oh, it should be capital Q. All right, well, P over Q, well, capital P is from up here. Capital P is B to the P. Capital Q is B to the Q. So we have b to the little p over b to the little q. But we know from our exponent properties that when we divide powers with the same base, we just subtract the exponents. So b to the y from over here is going to become, or we can write this as b to the p minus q, because we subtract when we divide. So dividing, we subtract the exponents, okay? And so now y is equal to p minus q, and we end up with the same little p minus little q. Let's finish off with some substitution from up above. We know what little p is and little q is, so let's put the logarithms back in there. Log base b of capital P minus log base b of capital Q. Okay? And there is our second property of logarithms. When we are dividing inside the logarithm, we can write that as the difference of two logarithms there. Capital Q there. All right, and last one, what happens when we have an exponent like here, 3 to the 5th, p to the c. Let's generalize this and see what we end up with. So we have, in exponential form, we have b to the y equals p to the c. But p, capital P here, right here, is b to the little p. All right, I know I get a little tricky with the capitals in the lowercase, but hang in there. B to the y equals b to the little p, that's a little p, to the c power. So this c right here goes to here, and I'm replacing this capital P with b to the p. Okay, well, this is just, we can say b to the y equals b to the pc. So that tells us that y is equal to p times c. I'm going to run out of room here. Then lastly, we're going to substitute what little p is. Little p is log base b of p. So let's substitute one last time here. So that gives us down here, we have y equals log base b, if I can squeeze it in here, log base b. Let's bring this on over here and do our substitution over here. We end up with substituting for p, we're going to have y equals, and little p is equal to log base b of capital P, and I'm going to put that little times c here. All right, and there's our last one. So our last one we have right here. So three properties. When we are multiplying inside the log, we can write it as the addition of two logs. When we are dividing inside the log, we can write it as the subtraction of the two logarithms. When we have a power inside, this little c can actually be pulled out in front and become multiplying. And there, it all comes back to the exponential equations as we saw here. And now with these properties that we just explored and proved here, let's use these. Before we use the definition of a logarithm to find these solutions, the problem is here we have different bases now. Okay, and so this is a base 5. It's not base 10. This is base 4. So we have different problems. Well, what we're going to do now is let's think of this a little differently. And let's take the logarithm of both sides. If we take the log of both sides, and you can do this with a natural log or a log base 10, let's just take base 10 log. So log of 5 to the x is equal to the log of 2. And we're allowed to do that as long as we do it to both sides. Well, our power rule here tells us this x can go down here. And so this can become log, throw the x out in front, x times the log of 5 equals the log of 2. Remember, these logs are just numbers. We have the x out in front now, so we can divide this off. Divide by the log of 5, divide by the log of 5, and now we have our answer. The exact answer is x equals log of 2 over log of 5. Okay, there's an exact answer. If we want an approximate, we can use our calculator to find out by dividing these. Then we end up with about 0.431. Okay. All right, well, let's try this next one here using our properties of logarithms. All right, so let's do the same idea now. Let's take the log of both sides. And we have log of 10 times 4 to the x equals the log of 25. All right, well, we can rewrite this as a sum, because if we have a log of a product, we can rewrite it as a sum. So this is the log of 10 plus the log of 4 to the x equals log 25. Well, log of 10, this is just saying 10 to what power equals 10. That's what this question is asking. And the log of 10 is 1. So this is 1 plus, and then let's go ahead and bring this exponent here. Let's take this exponent, drop it down in front. And so this is x log of 4 equals log 25. Okay, and subtracting 1 from both sides, we get x log of 4 equals log 25. Dividing by the log of 4, we get our answer. So x is log 25 minus 1 all over log of 4. Okay, and if we want an approximate solution, we can go to our calculator. X is approximately 0.661. Be careful with your parentheses when you type this in your calculator. All right, and one more here. We have base e. So in base e, we definitely want to use the natural log here. And so here we have the natural log. Take the natural log of both sides, e to the x equals the natural log of e over 2. Okay, well, let's drop our x down here, and then we got the natural log of e. And then use our subtraction property here, natural log of e minus the natural log of 2. And the natural log of e here is just 1, because this is saying, remember the base is e. E to what power gives us e? Well, it's e to the first power. And so this is just 1 here. And so this whole thing becomes 1, big 1. So it just cancels basically, and x equals, this becomes a 1 minus the natural log of 2. And that's our answer exactly right there. We solve for x. If you want an approximate, we can get that. We end up with 0.307. All right, so that's how we use the properties. One last little rule to look at, and this is the change of base. If we have a log base b, and we want to be a log base a, in other words, we would like it to be log base 10 or e usually, we can take this logarithm and we can break it into two logs that are divided. And we won't prove this right now, but we can take the log of the x over the log of the base b. And notice we choose whatever we want this to be. So that works nice because using that rule here I have log base 2 to the 5th, or of 5. I can't use my calculator for that because my calculator doesn't do log base 2. So according to the rule that we just have up here, according to this change of base formula is what we call it, we can take the log base 10 of 5 over the log base 10 of 2. Now remember, I'm not writing the base here because when there's no base, we understand it to be base 10. And we can use our calculator to figure out what that is now, because our calculator does log base 10. And this gives us 2.322. All right. You can also do this with natural log of 5 over natural log of 2, because the base now is e, and we're allowed to choose whatever base you want here, and you'll end up with the exact same thing. All right, you try these other ones, and then pause this and come back and see if you get it right. And here we go. This is what we got. First one here, 3.024. Which means 5 to the 3.024 power gives us about 130. And if you think about it, 5 to the third is 125, so that sounds right. 0.431 for the next one. 5 to the 0.431 power gives us 2. And 0.861 for the last one. 0.5 to this power gives us 4. So that's how we can change base. So we now know how to change the base. We can deal with any logarithm. We can use these properties of logarithms, these rules here, so that if we have a product, we can write it as a sum of two logs, a division, a quotient, we can write it as a difference, and a power within the log, we can write it as a c, that power times a logarithm. And we can also use the definition of a logarithm to rewrite an exponential equation. And so we see two ways to solve exponential equations, using, like these guys here, using the definition or using the properties. And that is how we can solve exponential equations. So good luck and have fun with those logarithms. Remember, the log is the power.